Okay, so let's talk about capillary action, okay? So capillary action is the tendency of a fluid to be raised or suppressed in a narrow tube, okay? This is the narrow tube, okay? Of course, I draw it in a way that maybe it's too fat, okay? But then this is a capillary tube, okay? This is a capillary tube, which is a very tiny, a very narrow tube, which is due to the relative strength of cohesive and adhesive forces, okay? So you still remember that the contact angle, right? So the contact angle is the angle between the object surface and then the water surface, okay? So this is water, this is mercury, Hg, okay? Okay, so you see this is a concave meniscus. This is a convex one, okay? This is a convex meniscus. Okay, and then you have to know that the contact angle here is actually an acute angle, which means that the range of the angle is between 0 and 90 degree. And then this contact angle is an obtuse angle, which is from 90 degree to 180 degree. Okay, you still remember that the surface tension of mercury is larger than the surface tension of the water. Okay, like I said, in fact, other than mercury, water has the greatest surface area of any liquid. Okay, so you know that mercury has the highest surface tension, and then the second goes to water. Okay, so you know that the surface tension of the mercury is much higher than that of water. Okay, so you know that the cohesive forces between the Hg molecules is much greater than the cohesive forces between water molecules. Okay, and then if the surface tension effect is really obvious, then you can see that actually the liquid will try to retain some spherical shape, okay, because the droplet refuses to be spread out, okay? The droplet refuses to be in contact with the surface, okay? So you know that for this case, the adhesive forces between water molecules are greater than the cohesive forces between the water molecules and the glass molecules, okay? Glass molecules here and here. So for this case, right, you know that the cohesive forces between Hg molecules is greater than the adhesive forces between the Hg molecules and the glass molecules here, okay? Okay, let us draw a force diagram. Actually, the contact angle between pure water and glass is almost 0 degree, you know, so that you know that the surface tension force will act almost exactly upward, okay, like this, okay? You know that the angle is 0 degree. And then the contact angle between the mercury and glass is about 180 degree, okay? And then you actually know that the surface tension force is acting downward, you know, okay? So the blue color one is your net surface tension force, okay? This is your net surface tension force, okay? Okay, so you know that when the net surface tension force is upward, the forces will bring the water up, okay? They will raise the water. And then when the net surface tension force is downward, then what will happen is they will suppress the mercury, okay? They will suppress it to a lower level, and then we call these capillary actions. Okay, do you still remember that when you only have one interface, the pressure inside the bubble will be greater than the pressure outside the bubble by this volume, 2 gamma over r, okay? So you remember the pressure inside the circle is always greater than the pressure outside the circle, okay? For example, let's take a look at this. Now you draw a circle, you know, you draw a circle like this, draw a circle, this is a circle, right? So inside the circle, the pressure inside the circle is greater than the pressure outside the circle. okay, by 2 gamma over r, and then the r is the radius of the circle that you draw. Okay, the radius of this circle is capital R. Okay, so now this is a circle, this is a circle, and then you know that the pressure inside the circle is always greater than the pressure outside the circle by a certain volume. Okay, and then once again the R is the radius of the circle you are drawing. Okay, okay, so let's derive something. Okay, yeah, this is water, and then this is your capillary tube, and then you know that the water will be raised. Okay, oh, so you draw a circle here. Okay, the circle is exactly the meniscus here. I mean, the meniscus is just an arc of the circumference here, of the circle here. Okay, okay, so first of all, the radius of the capillary tube is small r, and then the radius of the circle that you have drawn just now is capital R, and then r cos theta equal to r. Okay, the theta here is the contact angle, you know. Okay, when you draw this line, which is the tangent line to the water surface here, and then you also draw a line from the center of the circle to here, to the point in contact between the water and the glass. So you know that you have a right angle here, and then actually the contact angle is exactly the angle here between the capital R and the small r, and then this is a right angle triangle, so you say that capital R cos theta equal to small r, and then the height of the water being raised up is h. Okay, the density you are using here is the density of water, which is 1000 kilogram per meter cube. Okay, so remember what I said just now. The pressure inside the circle will be greater than the pressure outside the circle by a certain volume, which is 2 gamma over r, because you only have one interface here. Okay, if you have two interfaces, then that will be 4 gamma over r. Okay, so now this is pressure at point A. The point A is just outside the water surface. Okay, so you know that pressure at the point A is the pressure of the atmosphere, and then you assume that the density of air is almost zero, so that I can say the pressure at point C is almost the atmospheric pressure. If not, if rho A has some very big value, then I have to say that PC is slightly greater than PA, you know. Because I have to say that PC equal to PATM plus rho A GH. Okay, I repeat one more time. I should say PC equal to PATM plus rho A GH. But then I said that rho A is negligible, so we just ignore this term. We say that this term is 0. Okay, so that's why I say pressure at point A and point C, the pressures are all atmospheric pressure. Okay, and then the point C is at the interface, you know, at the interface in between the water and the air. Okay, and then PC equal to PB plus rho GH. Okay, rho GH is the water pressure here, and then you say that rho C equal to PC equal to PB plus rho GH. Okay, the water pressure. And then by using all those formulas 1, 2, 3, 4, 5, you can eventually arrive at the height of the water, which can be brought up, which can be raised in your capillary tube. Okay, or you can choose to use force method. Okay, you say that the surface tension force in the upward direction is exactly the same as the weight of the water that you have raised. Okay, so once again you find out your effective length and then your surface tension force, and then you resolve it to the upward direction, and then you find out the weight of the water that you have raised up. Okay, so you still can arrive at the same formula. And then you remember that since the contact angle is an acute angle, cos theta has a positive value. So you say that the height of the water has a positive value. So you know that you actually bring the water up, okay, not downwards, okay. So by the same reasoning here, let's take a look at the mercury. So you know that the mercury will be suppressed, okay. And then like I said, you draw a circle here. The radius of the circle is capital R. The radius of the capillary tube is small r, and then you say that r cos theta equal to r, okay. I won't draw the same diagram like just now. You go and find out yourself, okay. So you know that the pressure inside the circle is greater than the pressure outside the circle. So you say that PB equal to PA plus 2 gamma over R, and then remember the R is the radius of the circle, okay. And then PA and PC, they are all atmospheric pressure. And then like I said, you assume that the density of air is almost equal to 0, because if not, then you have to say that PA equal to PATM plus what? Plus rho AGH, okay. Okay, but then this is we just ignore it, okay. This is negligible. And then yeah, so remember PB equal to PC plus rho GH, okay. The rho here is the density of the mercury. And then you use all those 5 formulas, you can arrive at the exact same formula, okay. Or you can use your force method, okay. I won't repeat the step, you just refer to this. You use the force method. And then once again, you know that the contact angle right now is an obtuse angle. So you know that cos obtuse angle has a negative value. So you know that H is a negative value. So you know that the mercury is suppressed, okay. It is pressed downwards, okay. And then remember, this is the formula that you have obtained, right? H is directly proportional to gamma. So you say that the greater the effect of the surface tension, the more suppressed the mercury will be. That means that if gamma increases, then H increases, okay. The mercury will be suppressed even more. And then H is inversely proportional to rho, because you know that the greater the density, right? The greater the density, the greater force you will need to bring the water up. Or you can say that the greater force you will need to suppress the mercury, okay. So when the rho increases, H will decrease, okay, because when water gets very heavy, it's more difficult to bring the water out, right, okay. And then yeah, H is inversely proportional to R. So you know that the smaller the tube, the greater the effect of your capillary action, okay. The smaller, the narrower the tube, the greater the height of the water that can be raised, okay. So now let's do a question. A U-tube with different limb diameters is shown. At equilibrium, water with level difference is observed in the 2 limbs. Given that the surface tension of water is 7 times 10 power negative 2 Newton per meter, okay, and its density is, the density of the water is 1000 kilogram per meter cube. And then if the contact angle is 0 between the water surface and the limbs, what is the difference in the water level? So what is the H here? The difference in the water levels, okay. So contact angle equal to 0. R cos theta equal to R. So you say that, oh, the R exactly as the R here, okay. So you know that the circle is right exactly in the limb, you know. I mean the circle is exactly just nicely within the tube, okay, like this, okay. Okay, so like I said, you draw a circle here and then you draw a circle here, and then the pressure inside the circle is greater than the pressure outside the circle by a certain amount. and then you say that PD equal to PB equal to atmospheric pressure. Once again, you say that, oh, the density of the air is almost equal to 0, okay? So that you don't have to say, oh, PB equal to PATM plus rho air GH, okay? And then, yeah, PA is equal to PC plus rho GH. So by using those 5 formulas, you can get your answer, okay? Yeah, so you settle this at home. Two rectangular blocks are placed in water. Due to surface tension of water, some water can be pulled out in between the blocks. Given that the surface tension coefficient of water is like this, the length of the block is 10 cm, the separation between the blocks is 0.2 mm, the density of water is 1000 kg per meter cube, and then the gravitational acceleration g is 9.8 meter per second. Please find out the height of water in between the blocks. So once again, you use the formula surface tension force equal to gamma times the effective length, which is equal to the weight of water being pulled out, okay? So the effective length is what? Is 2L, okay? The length here, and also the length here, okay? Which is the length here, and the length here, okay? Okay, so, yeah, the weight of the water being pulled out is rho Vg, and then the volume is what? Is here, okay? Is D times H times L, okay? So you can know the height of the water that can be raised in between the two parallel blocks, okay? So in the next video, we are going to talk about viscosity. Thank you.